Okay, before we get too far, I want to remind you of something. So let's start from the beginning. I want you to find 3 points, right? How do I know where I should plot any of the points for this function? How do I find points for this function? See, the other 4 of you are not. I'll just by looking at your papers. How are we going to find a point for this graph given this function? Input, output, right? Input and output, that's what a function is. Put something in, get something out. Okay? So I see this on several of your papers. Okay? So we choose to plug something into the function. What can we plug into the function?
0. 1.
What's that? Anything we want to plug in there. Okay? Anything we want. What's a really easy one to plug in?
0.
0, super easy. Couldn't get easier, right? Easiest of all inputs is 0. Because 5/8 times 0 is?
0.
And we subtract 2 from 0. -2. Couldn't be any easier, right? So we have a point, 0, -2. Great, good place to start. And again, we can plug anything we want in there, like 1, 2, or 3. And I know it's been quite a few days, because one day got canceled, and been a weekend in between now, and the last time, it's been a long time since we've seen each other, but we did establish that some numbers are easier to plug in to this function than others. What numbers turn out to be a lot easier to plug in for x than others?
Numbers that go into it, so like 5, 8, like 8 can use 4 or something like that.
Oh, numbers that go into that number?
Oh, I'm just giving an example like that.
Okay, let's look at 5/8 times 4 minus 2. So 4 and 8, they share a factor of 4. This is 2, that's 1, so we have 5/2 minus 2. So a little bit helpful. Then I have to get a common denominator here, that's 5 halves minus 4 halves. 5 halves minus 4 halves is 1/2. So if I plug in 4, I get 1/2. Is there anything that's even easier than 4?
1, 5.
5, 1. Other suggestions?
8.
8. Why 8? Because the denominator is 8?
Yeah.
Let's see if that actually pans out. Multiply this by 8. Let's put 8/1. What happens when I multiply something with a denominator of 8 by something with a numerator of 8?
They cross cancel.
Right? 8 divided by 8 is 1. 8 divided by 8 is 1. So we just wind up with what? 5/1. 5 minus 2. No more fraction. Right? 5 minus 2 is just 3. Look at that. That was a lot easier, right?
Would you divide 2 or subtract 2?
This 2?
Yes.
Well, it's minus 2, so we would subtract 2.
Okay.
5 minus 2 is 3. What's another number where this nice thing will happen again?
10.
What's that?
10.
10. If I put a 10 there, it'll cancel, it'll have common factors. What about just completely canceling out this 8? Instead of just sum of it, and still having a fraction like 4 did, 4 canceled out the 8 sum, like it did have a factor in common. But 8 canceled it out completely, turned it into a 1. Is there another number that will cancel with the denominator of 8, turn it into a 1?
60.
16. Let's see, let's cancel, let's cross these out here. There's 16 there. Do 8 and 16 have a common factor? What's their common factor?
16.
That's not
Sorry, 2. 2.
Well, even bigger than that.
4.
Bigger than that.
8.
8. Right? That very number there is the common factor between 8 and 16. That's nice because when you divide this by 8, you get 1. So there's the denominator is now 1 straight across. Now, when we cancel an 8 from 16, divide 16 by 8, we're left with what?
2.
2. Not 1 this time, but 2. 5 times 2 is 10. 10 minus 2, 8. So we plug in 16, and we get 8. What's another number where that's going to happen?
It's just on double.
Doubling?
Yeah.
So what will be the next one?
Four.
What's that?
16, 4.
24.
24, you think? 24, let's see. Well, do 24 and 8 have a common factor?
30.
Yes.
What's their common factor? 24 and 8, their common factor is?
3.
8 has a factor of 3?
32.
Their common factor is 32? I'm asking what their common factor between 24 and 8 is? 8? They will have a factor of 8? Can't get any bigger than that. That's 8. That's everything 8 has to offer. 8, cancel, well, divide this by 8, you get 1. Divide this by 8, you get
3.
3. First we got 1 when we plugged in 8. Then we got 2 when we plugged in 16. We got 3 when we plugged in 24. 5 times 3 is 15. 15 minus 2, 13. And then, Noah?
32.
32. And after 32?
40.
40. And after 40?
44.
48.
48. After 48?
56.
After 56.
On and on and on and on.
On and on. And what kind of a pattern?
Right.
By 8.
By 8. So the next multiple of 8. If you plug a multiple of 8 there, it'll have a factor of 8 in it, and it'll cancel that 8. Right?
Yes.
You don't have to plug those numbers in, but they are the easiest ones. We start to notice this pattern that we call the slope of the graph, because the graph is, it happens for this kind of a function to be a line. We have 0, -2, we have 8, comma 3. How about in this direction? Is there a number in the negative direction we can plug in to make it an easy outcome?
Negative 8.
-8. 5/8 times -8. 1 minus 2. 8 divides 8, leaves 1.
0. Wait, not 1. Negative 1.
-1, very good. 5 times -1 is -5, minus 2, -7. So
Woo.
-8, -7.
Not for the board.
We're importing the whole thing. -8, -7, there it is. So look at these 3 points. They seem to be all in a what?
So straight line.
A straight line. All in a straight line, it seems. Okay. Are these the only points that exist for this graph?
No.
No. How many exist for this graph? No.
Infinite.
Thank you, Noah.
Yeah.
Sorry.
So how many points exist for this graph? Infinite, an infinite number. Okay. If I plug in 1, can I plug 1 into the function? Is it possible? Is it allowed? Certainly it is. Will there be some output? Yeah. Let's see what the output would be and see where that point would land. We'll plug in 1 now. 5/8 times 1 minus 2, that's 5/8 times 1 is 5/8, so minus 2. Now we need 8ths to 16/8. 5/8 minus 16/8, that's -11/8. That's -1 and 3/8. Okay. So 1 and -1 and 3/8. 1, -1 and 3/8 is going to be right in there. Does this one seem to be on the same line that the first 3 looked to be? Does look that way. Are you surprised? I hope not. Okay, let's try plugging in 5. Let's see what happens when we plug in 5. Actually, you guys do that. Plug in 5. Oh, I should have never raised that. Plug in 5. see what I get for my output, and then we'll see where that point lands. How many points could we possibly find, theoretically? An infinite number. It would never end. Okay, so if you plug in 5, we get 5 over 1. When you multiply by 5/8, you get 25 over 8. We need a common denominator to subtract 2 from there, so we get 16/8. Root over 1, multiply by 8 by 8. 16/8. 25/8 minus 16/8 is 9/8. Okay, which is 1 and 1/8. So 5 gives us 1 and 1/8. There's that point there. Estimating about how much an eighth would be. Does that seem to be in a straight line with the other ones as well?
Yeah.
It certainly does. So, this graph, certainly believable. It's easy to trust that it would be a line if we were to plot all of the points. How many are there? How many points?
Infinite.
An infinite number of points. If we were to plot all infinity points, we would get so many of them, they get all mushed together and get so close that we not even see any gap between the points anymore, and they would make what kind of a shape?
Straight line.
Straight line shape. So, when I do this, and I start to draw this line, what am I drawing, really?
Bunch of dots.
Bunch of dots. In fact, because they're on this computer screen, that's exactly what they are. That's the way computer screens work, right? It's a bunch of little dots. Little dots we call what? Pixels, right? So it every time I drag my pen across here, it fills in another pixel, right? Fills in those pixels. I'm trying my best to plot all of those points. That's really what I'm doing. Except for, why don't I actually go in there and fill in all of these dots, like one by one? Because I would die before I finished with this one math problem. I have things to do with my life. So I'm gonna just draw a line through all these points and say, this is what it would look like if I were to fill in all those points. They would just make this line. So this graph, or any graph, is really a guess. It's a guess. Do you agree? What are we guessing at?
It just keeps going. Forever.
That it keeps going forever? I guess that's my putting an arrow on there is my
Both
guess.
ways.
Keeps going both ways. Quite what I'm guessing at. What am
You're guessing on what the function
What?
Well,
will look like
by drawing this line, okay, kind of, yeah, what y equals for this x, right? Like right here is a guess for where I think this point would be. Right? If I were to plug in this x of 9.9, I think the y value would be something like 4.2 or 4.3, right? So this whole thing is a guess at where all of the dots or points are going to be. Okay? Guessing where all of the other points are going to be. I don't have time, I don't have infinity time to plug in all of those x values and find all of those y values and plot them all. Right? There's an infinite number of points between here and here. Just between those 2 points there's an infinite number of points. Just don't have time to do it. It's not feasible. So we guess and we draw this graph. Okay, so graphing then becomes, do I know what shape it would come out to be? In this case, we do. It would be a line. Okay? And any function that can be written like this, a number times x plus a number, will be a line. The graph will be a line. Okay? So then it becomes finding the, like kind of a game of finding the least number of points necessary to figure out where that line would be. Right? How many points do you need to find in order to draw a line?
2.
2. That's it. It's the least number that we could find. We could find more, but we just be kind of redundant. We just keep finding more points that are on the line that we could draw between the 2 points that we find. Right? We'll talk more about that in a minute. But I want to talk more about graphs. Okay? Let's just charge ahead with graphs so that you can understand graphs in general, so that they don't seem intimidating. Okay, so let's look at First,
Oh, jeez.
this function here, I want you to fill in the table for this function, okay? It's gonna take a few minutes. Get out your calculator, make sure you keep all those negatives straight, all right? Make sure you're doing all that correct. And we'll see where we are in a few minutes. Okay, let's try plug in 2, and we'll do a negative. So let's plug in 2, we get 2 times 2 cubed minus 3 times 2 squared minus 5 times 2 plus 6. So let's look at this 2 times 2 to the third power. I'm going to take this 2, I'm either going to take it to the third power or I'm going to multiply it by 2. Which should I do first? Why should I take it to the third power before anything else? Why shouldn't I multiply 2 by 2 first and then take 4 to the third power?
Because there's 3 2's already there. I mean, like, you can't do, it's like combining oranges things, it just doesn't make sense, because this is a product of, I know, the 2 part of the 2 to the third power. And if you do it that way, I don't even know where I was going with that.
Yeah, I see what you're saying, I think. But, I mean, 2 different people approach this problem. One of them does it this way. 2 times 2 times 2 is 8, and they do 2 times 8. Another person takes it and multiplies 2 by 2, gets 4 to the third. 4 to the third is 64. 2 times 8 is 16. So one person gets 64, the other person gets 16. They can't both be right. So why are we supposed to take 2 to the third power and then multiply by 2, as opposed to taking 2 times 2 and getting 4 to the third power and getting 64?
People agree to do it the other way.
Okay, we all agreed to do it this way, and if you remember, it's just order of operations. Okay, this 2 is either going to get raised to the third or it's going to get multiplied by 2, according to the order of operations that we all adhere to. Exponents comes before multiplication and division. So we're going to exponent this 2 before we multiply by 2. If we were to multiply 2 by 2 and get 4, we'd be doing multiplication before we do exponents. Okay? Like, we could do it that way, that could be the way that we do it, but it turns out it's not the way. It's not the order that we all agreed to do it. Okay, so we should get, in this first part, 2 times 8, which is 16. Okay. Then we get negative 3 times 4. 2 times itself is 4. Negative 3 times 4 is negative 12. Negative 5 times 2 is negative 10. 6. Negative 10 plus 6 is negative 4. 16 minus 12 is 4. Minus 4 is 0. So if we plug a 2 in, we get a 0 out. Same thing, but we'll do it for a negative 2. Right. Negative 2 cubed, negative 2 squared, negative 2 times negative 5.
Excuse the interruption, please release the girls' soccer team. Please release the girls' soccer team. Thank you.
So what does it mean to take a number to the third power? Once again, another reminder.
Multiply by itself 3 times.
3 times. What is the number that we're going to multiply by itself 3 times here, Cameron?
-2.
Negative 2. So what's negative 2 times negative 2 times negative 2?
Positive 8.
Well, these two together are positive 4.
Positive 28.
Yeah. Wait.
-8.
Yeah, negative.
And 4. This 4 times negative 2 is negative 8.
Wrong one. I was doing it wrong.
2 times negative 8. What's negative 2 squared?
4.
Positive 4. Negative 2 times negative 2, that's 4. Negative 3 times 4 there. Negative 5 times negative 2.
10.
Positive 10. Negative 10 negative is positive. Plus 6. Negative 16 minus 12. Plus 10 plus 6 is 16. This is nice negative 16 plus 16 is 0. So they cancel each other out and you're just left with a negative 12. There's plenty of room here to get confused. My recommendation is always to put a parentheses there, then plug your number into the parentheses, and then do exactly what you should do in the order that we agreed to use, and work it out that way. It makes it less likely that you'll make a mistake. Erase all of that. Okay, now that we have those, let's plot this information on the graph as points. I'm gonna move this up a bit so I have enough room for that negative 12. So negative 3, negative 60, I don't have nearly enough room to plot that, so I'll leave that out. But negative 2, negative 12 I could fit. There's negative 11, negative 12 would go right about there. Negative 1, 6, 0, 6, 1, 0, and 2, 0. Here's the challenge to you. I want you to plot these points just like you see them here, okay? Plot that guy there, these two here, these two here, okay? Do that. I'll tell you what I want you to do next. So the next thing that I wanted you to do, now that you have those points there, let's go back to this graph, this line. Okay, remember how we came up with the graph of this line? We plotted these select points here. Actually, we started with this point, and this point. And all those points seem to be in the shape of a line. Then, just to drive the point home, I plotted some more points. One there, one there, one there, right? Actually, that was a guess. We actually did the work for this one, and I guess just those two. And they also seem to be on that line that those first three were implying, okay? And then we drew that line, just kind of saying they look like they're all going to be in a line. If I went on forever, went every 8, right? I went over 8 again and plotted that point. It certainly seems like it would be in a straight line, and the other direction would be in a straight line. So we make our guess that all the points are going to form a line if we were to graph all of them. Okay? How many points can we plot for this graph?
3.
Well, theoretically, how many are there that exist?
Infinite.
An infinite number, right? I could plug in any number I want and get out a number. Okay? I'll never not get an output if I put an input into this function. Some functions aren't that way, but this function is. You can plug anything you want in for x, and you'll always get something out, which is what can be represented as a point. All right? So this next thing that I want you to do is to draw the rest of the points, or the graph, right? Draw the graph. I want to see you draw the graph. Is it going to be a line? Is it going to be a zigzaggy thing? What's it going to look like? Okay? And then I'm going to remind you about this graph and how it came to be and how this would have to come to be in a very similar fashion. Not similar, then it would be a line. Clearly not a line, right? These are not in one straight line. Agreed?
Agreed.
Okay. So we're not going to have one line to
Yeah,
capture all
true.
these points. We could. Would that be it? Is that what this graph is going to be?
You, can you take classes to bump you up level? Like
Me?
a math schedule level?
You're talking about me or you?
Me.
Can you take classes to bump you up a level?
Yeah, like instead of going up to geometry next year,
Uh-huh.
if I can like take a test, take it up into pre-calc.
Take you up to pre-calc? That would be a tough leap. I'd say algebra 2 would be a good place to go.
Yeah, I know.
And then pre-calc.
That's just an example.
You'd have to talk to principals and counselors. They decide those things. Okay, so I see a few different possibilities. Let me throw one up there. I saw a couple lines like that, and then I think like that. Okay, what we have to keep in mind, what we're trying to find is the graph of this function, right? What's the graph of any function made of?
Input, output.
Input, output, which we turn into points or dots, right? And how many dots and points are there that exist? An infinite number, okay? So if this is the graph of that function, what we're saying is that these lines are the mushed up, melting together points that we would plot if we plotted all the points. Does that make sense? If we were to plot all the points that exist for this function, all the inputs and outputs, and all those points would get so close together over an infinite amount of time that they would start to look like this right here. Okay. So let me ask you a quick question. If I put into this function, if I put a 0 into this function, what do I get out? And right over here,
Get
Oh,
6.
you get 6. If you plug in 0, you get out 6. Plug in 0, you get out 6. And that's why this point is here, right?
Correct.
That's why this point is here, correct?
Correct.
0, we put in 0, we get out a 6. Okay? Well, supposedly this graph is made of all the other points that we didn't have time to plot, right? Well, according to this graph, there's also a point right there, right? There's also a point right down here. I want all your eyes looking up here, because I'm making a point that later you're going to not understand, and I'm going to say, weren't you paying attention? You're going to say, no, I was doing something else. Okay? So according to this graph, which is made of an infinite number of points, there's also a point here. Agreed? There's also a point here, according to this graph. Because this graph is made of an infinite number of points. Okay, so this point is at 0, 6, which we've already discussed means it's saying about this function, if you plug in 0, you get out 6. What's this point saying? First of all, where is it?
At that negative, 3. What am I talking about? 3.
Give me the full coordinates.
0, 3.
0, 3. So what's that saying about the function?
It's going up 3 and over, right?
So it's this point where it is,
You put
these two
0, you
numbers
get out
being its
3.
coordinates, you put in 0, you get out 3 is what this point is saying. Is that true for this function?
Correct, yeah, that is.
It's true for this function. If I plug in 0, I get out 3.
No.
No.
If I plug in 0, I get out what? 6. Maybe if you try it again. Try plugging 0 in again. You get 12 this time? What will you get if you plug in 0 for this function?
Is it 9? 6.
Will you get 9?
9.
Let's plug in 0 again. 0 cubed minus 3 times 0 squared minus 5 times 0 plus 6. 0 minus 0 minus 0 plus 6 is 6.
Right.
Let's try it again. 2 times 0 cubed minus 3 times 0 squared minus 5 times 0 plus 6. This time, we got 0 minus 0 minus 0 plus 6, which is 6 again. Should we try it again?
No, it's going to be 6.
It's
always.
gonna always be 6. So what about this point? If you put in 0, you'll get 3. This point says
It's a lie.
it's a lie. Yes. Is this point a lie?
It's false.
I just said it was, so yes, it is a lie. You do not get 3 when you put in 0. What is this point saying?
You put in 0, you get out -5.
You put in 0, you get out -5. That's what this point is saying. So what do you think about what this point is saying?
It's also a lie.
Also a lie. The only one that's true is this one. You plug in 0, you get out 6. See what I'm saying? Could this point be on the graph for this function?
No.
Why can't it be on the graph for this function?
Because you put
0 always.
equals
0 in, always 6 out. 0 in, 6 out. For this function, 0 in, 6 out. Never anything else. Only 6.
All right.
So could this point be for this graph? The graph for this function? This point right here? Right here? 0, 3. It couldn't be. Because it's saying you put in 0, you get out 3, which is a lie. This one's also saying if you plug in 0, you get out -5. Could that possibly be true?
No.
So could this point be on the graph of this function?
No.
No, the only points that could exist for this function are, well, for 0, the only y value that works is 6. So for a point that has an x of 0, the y has to be 6 for this function. No other y will do. So no other point with x of 0 could exist for this function, except this one.
Okay.
So that can't be. So maybe I'll just erase that one little point. That can't be right, and this one can't be right. Okay. You think it's just those points that aren't going to work out? Probably the ones next to those ones as well. Right? The only points we know for sure that work are the ones that we actually put in those values and got out, the y values. Okay. So this graph, giving some points correctly and some points are lies, that can't be right. So let's just go back to what we know is right. We did plug in this x value, we did get out this y value, we plotted those points, we're sure those points work. You wanna continue to do as well as you're doing so far in this class?
Yeah.
Okay, keep
I
going.
just, I felt my wisdom teeth. Kinda hurts.
Okay. And that point. So we know these points will work, they are true. We did put in those x values, we got out those y values. So that graph doesn't work. What about this graph? I saw one that was, I think, like kind of similar, like this.
Oh, I hit a little.
That, something like that. Will that work? Could that be the graph for this function?
No.
Why not?
Correct.
Like the other one, but kind of change just slightly. There's still gonna be lies on it.
Lies, yes, lies upon lies upon lies. It couldn't possibly be that this is a point on the graph and this is a point on the graph. Also, it can't be that this is a point on the graph, which we know is a point on this graph, and this one is too. Because they both have the same x value, but they have different y values. If I put in a certain x, we're going to get out the same y every time. If I put in 2, I'm going to get out 0. If I put in 2, I'm never going to get out 2, which is what this point seems to be saying. Put in 2, get out 2. That doesn't seem like it's never going to work. That's a lie. And there's just an infinite number of lies, right? In addition to that one. See what I'm getting at? I know that this cannot be the graph for this function because I know some points for sure, and there's a bunch of points that this graph is saying are there that couldn't be there. It can't be there. So, that can't be the graph. Okay. Let's just start here. Let's look at this point and this point. Are there points in between those points? Okay, let me ask it another way. This point is here at -2, -12. And this point is at -1, 6. Okay. This -12 is what you get when you plug in -2. This is what you get when you plug in -1. -2, -1. Could I plug in numbers between -2 and -1?
Oh, there is some numbers between negative 1.
There aren't?
Well,
There's
like negative
there's a lot of
1.5.
Okay, that's a number. Right? And it may not be very convenient to do, but is it possible, theoretically possible, to plug -1.5 into each
No.
of these x values?
No.
Not theoretically possible?
Maybe, I don't know.
Well, let's just write it down and ask ourselves, is this gonna, like, is anything bad gonna happen? Is it gonna be impossible to do this? Difficult, maybe, time consuming, maybe, but is it impossible
It's
to
not
take
impossible.
-1.5 to the third power?
No.
And then multiply by 2, whatever you get? No, can we take -1.5 to the second power?
Yes.
Yeah, -1.5 times -1.5 is positive 1.25.
Somewhere around there.
That's right. 3.9. Well, yes, you can do it. 9/4. Can we multiply that number by -3? Yes. Can you multiply -5 by 1.5? Sorry, -1.5? Can you add 6 to that? Yeah, so it can be done, right? So there is an output for the input of -1.5. It is possible. Like it's right there, -1.5. There is some output for that input. Are you all tracking what I'm saying there?
Yes, I'm also.
Now, we know the output is -12 when you put in -2. We know the output is 6 when you put in -1. If we did put in -1.5, based on those 2 points that we already know, do you think the output for that one would be like 25? When I put in -1, I get -12. When I put in -1, I get 6. Do you think if I put in -1.5, the output would be 25, for example? It would be 25? Given the output that we know for this -1, or sorry, -2 and -1. That would mean that, well, if it wasn't a 25, then I would have a point that was way up there. Does that seem to fit the pattern we see between these 2 points? What's your guess for a better output for -1.5?
Somewhere between -2 and 1.
Between -2 and 1? You think it'd be between 6 and -12?
-1 and -12. I got 6 and -12 in between there.
You think it's somewhere between -1 and -12?
Not -1, sorry. +6 and -12, it has to be in between that because otherwise it won't be part of that.
So somewhere
Point track.
somewhere in here, there's a point that is -1.5 for the x. And you think the y value would be somewhere between -12 and 6.
It would have to be, or it would no longer be within like that whole boundary you kind of have set up for that. For the point you're trying to find, you go out of it, so we have to be in between them.
Well, I'll say that it doesn't have to be. It is. It doesn't have to be, but it certainly is something that I believe strongly. It certainly seems like it would be somewhere between here. It seems like the point, if this is my x value, then my y would be somewhere like right here, right? Or maybe here, or maybe that point is somewhere in here, I think. I don't think that that point is going to be way down here when the next point is right there that I know for sure. I don't think so. I'm not absolutely certain, but it just doesn't seem like what's going to happen.
Just like, set up the boundaries there.
Right. Here, just in case we're not sure. Let's plug -1.5 into this function. So, clear. Let's try.
Button stuck.
I guess. Well, let's put a little soda on or something. Okay, so first.
I just realized there's only infinite dots because there's infinite numbers,
Yeah. There's infinite numbers.
but it has to be infinite dots.
I'm never gonna not get an output if I give it an input. So the infinite numbers, infinite points. So let's see if we can, there we go. So here we go. 2, that's a decimal point, 2 times -1.5 to the third power, parentheses there, third power, minus 3 times -1.5 squared, minus 5 times -1.5 plus 6. So 2 times -1.5 to the third power minus 3 times -1.5 squared minus 5 times -1.5 plus 6. So the calculator follows the order of operations very strictly, so it should do this first, then multiply by 2 afterwards, so on and so on. I get 0. Interesting. 1 point. That's an interesting guess that you made there, RV. Because it gives us a 0 when we plug in negative 1.5. So, negative 1.5, comma, 0 is what it turns out to give us. It certainly seems to match what I thought would happen.
I think it might be like that because 6 is already half of negative 12.
Uh-huh.
In a way, it's still going to go negative 6, but since it's already half, it just being the dead center of the graph is where it ends up being. Because we can't.
Interesting theory on why that happened.
To me, it makes sense anyway.
Once we draw this graph, whatever we draw, it will be a guess, right? Well, okay, so now we split the difference between negative 2 and negative 1. At negative 1.5, we get 0, which is kind of cool. Okay. If I split the difference again between negative 1.5 and negative 2, I bet you that point would wind up somewhere in here. I bet you if I went between negative 1.5 and negative 1, I'd get a point somewhere in here. How about if I plugged in negative 0.5, negative 1/2? It's between negative 1 and 0. What kind of y value do you think I'll get?
Somewhere between those 2 points.
Somewhere between these 2 points? Well, if I go straight between these 2 points, that's just all at 6. Do you think all of the inputs between 0 and negative 1 will give me an output of 6?
Yes.
That would be pretty weird. Think about what that would mean. It would mean that if I plug in negative 1, I get 6. If I plug in negative 0.5, I get out 6 again. If I plug in negative 0.75, I would get 6 again. Like there's an infinite number of numbers that I could plug in between negative 1 and 0 that would give me out 6 every time. I just don't think that would happen.
Yeah. I was thinking, yeah.
Let's try switching out all the negative 1.5s for just negative 0.5. So I'll bring out this line again. Change the 1s to 0s. Negative 0.5, negative 0.5, 0.5. So I'm going to enter and I get 7.5. A little bit bigger than 6.
Nice. Gnarly.
So plug in negative 0.5 to get out 7.5. There's 6, 7, 7.5. It looks like this graph is going up like this, through that point there, up through that point. I bet you the graph comes back down to the point that we have there. Right? These are my guesses for the points. And then it comes back down here. And then what? It's got to get to this point, right? It's got to have that input-output combination at some point. I bet there's a bunch of points between those 2 points, and I bet there's a bunch of points down here. Does it go? Will it just keep going up forever and ever? Will it come back down? Do you think?
It can come back down, it can go wherever it wants because it's unlimited, remember?
Yeah. There's an infinite number of points. It does one of them. It doesn't do both. It does one of them. Does it go up that way, or does it go down that way?
It can go anywhere it
We
wants.
got to do more studies to find out.
We're gonna do more studies to find out. We're gonna have to plug in like a 3 and a 4 and a 5 and 6 and so on and so on and so on, and start to guess at what's gonna happen as I put in a bigger and bigger number.
Oh, yes, it goes.
So Branson, what do you think? Do you think it's gonna keep going up, or do you think it's gonna go back down?
I was thinking about how I just realized, like, the lines just make each other all up. Like, the reason why we got a line going, like how we're doing like that, the reason why that dot's even there, because that's the proper function and stuff for the other one. And that one's only there because I made up another line. So all the lines just make up each other. That's why they're like crossing and parallel and doing all that they're doing to each other. That's why some are a line for that function.
Uh-huh.
Because for that other line, you will get that as the thing. But that's why that dot is there. Because, yeah, for that function it's a line, but for the other function it's actually correct.
Yeah.
It's part of the line that wouldn't go across there if you drew it there.
Yeah, it's part of another function.
Yeah.
Yeah. So there's like you're kind of saying like there's all these
just crisscrossing.
invisible
Yeah.
points that we don't see that are parts of other graphs
Yeah,
or
they're
other
crisscrossing each other
functions.
so much that they form like these actual parallels and like things on
Uh-huh.
if you put the dots there.
Yeah. All these points that aren't being used are like some other parallel universe, are part of some other graph or some other function. Yeah. It's pretty weird.
That's a pretty intense conversation.
So, that's blew my So if we plug in 3, if we plug in 4, if we plug in 5, it turns out, because think about it, this cubing, right, is a number multiplied by itself 3 times. This is just times itself twice. Okay? If we multiply by a number by itself 3 times, like the number 5. Multiply the number 5 by 5 by 5, you get 125. It's a big number. And you might subtract off a little bit there, but it's just not going to be as big as, well, this would be 125 times 2, that would be 250. If you plug in 6, that's going to be 216 times 2, that's 432. If you plug in 10 cubed is 10 times 10 times 10, that's 1,000. Right? It just keeps getting bigger and bigger and bigger and bigger. Those outputs keep climbing and climbing and climbing and climbing. Those points keep having bigger and bigger and bigger Y values. They just go off towards these big positive numbers off the charts. Not this way, because that would mean that we get these really, really big negative numbers. That's not going to happen because we're plugging in positive numbers in here. This is going to be positive because there's a positive right in front of that 2. Right? So I bet that's what the graph for this function looks like. Because the points we already had, I'll bet the points that fill in the gaps are somewhere between those points. Or if these points are right next to each other, probably drop down below them, because it seems like that's what would happen. It's kind of a pattern we're seeing here. They drop below and then go like that again. So, that's what a graph is. A graph is made of an infinite number of points. When we draw that graph, we're guessing where the rest of the points will go. Don't put lies in there. Okay? So if there's a point right here that we're sure of, there's not going to be another point above or below that point, because that would mean that we have a different output for the same input, which can't be. It just can't be. That would be a lie.
And we don't like lies.
We don't like lies. Okay? Now that's what makes a function a function. There's 2 parts to being a function. Firstly, input and output. And we already talked about that. That's what we said toward the beginning of this class today. The second part, there's 2 parts to being a function. The second part is almost obvious. If I put in an input, right, into the function, I'm going to get 1 output. This is what we've been talking about this entire time. If I plug something into the function, I get 1 output. Not 2 outputs, not 0 outputs, not 3 outputs, 1 output. Put something in and I get something out, and I only get 1 thing out.
Because you can't get 2 different.
Can't get 2 different answers for a function. Now there are some things called relations that you can get 2 different outputs, but we're not even close to caring about those right now. Okay. Anything that you would make up with just x's and stuff randomly thrown in there, probably going to be a function. You put 1 thing in, you get 1 thing out. So this is a function. The line that we just looked at previously, that's a function. Right? There's a function. Every time I put something in, I get 1 thing out, not 2, not 0, not 3 things, just 1 thing out. Put in 5, I get a specific output. I put in 8, I get a specific output. I put in -6, I get a specific output. And this graph is my guess at what all those outputs are, because I'm asserting that there's points there, saying that those points exist. Okay, let's go back to these kinds of graphs, these kinds of functions that we call linear functions, as opposed to this is what we call a 3rd-degree polynomial function. And let's look at just a regular linear function. Okay, and what I want you to do, since you know it's a line when you find this graph, instead of plotting all these points and just seeing that they all just fall in a straight line, let's just say, I know because it looks like this as a function, that the graph will be a line. So I'll just need to find how many points? 2. Let's find 2 of the easiest points possible, and then say, okay, I know it's going to be a line. I'll draw a line between 2 points, and I'll know that that's where all the other points land. Because I know this happens to be a straight line. So let's do this function. Y equals 5/4 x minus 3. very little time, you should be able to come up with 2 points. Right? You want to find 2 easy points to tell you where this line is going to be. See, we need a little bit of help here. Let's find the 2 easiest points possible for this graph. Okay? We're looking for points. Points come from input and output. Input and output start with an input, so let's choose an input. Cameron.
0.
0. Okay? 0 is a great input. It is the easiest input of all inputs.
Can we start with 0?
Always.
Gosh, dang it.
You can always start with anything you want, because I just put it up to you. It was your decision. We can start with 0. It's pretty quick to see what's going to happen, what output I'm going to get when I plug in 0. What output will I get? 0. Now, 0 there. Minus 3, negative 3. Input of 0, output of negative 3. Here, quick quiz. For this function, what will I get when I plug in 0 to that function?
Plus 7.
What will I get when I plug in 0 to this function?
Plus 8.
What will I get when I plug in 0 to this function?
Oh, jeez.
Negative 2. I couldn't get any easier than plugging 0 in for x, because the thing that's multiplied by x, since x is 0, will go to 0. The other thing that's left is the thing that's not multiplied by x. Right? Let's back it up. Back it up. Okay, so that was a quick little quiz. Okay. How about, let's talk in generals, generalities. If I plug 0 into x for this function, what will I get? 0, b. So for any linear function, you're always going to have a point at 0b. 0b.
We should have the.
That's what we call the Y-intercept.
Oh, that's what it is? Seriously?
That's what it is.
Why did Parsons teach us this?
Because it's Parsons.
He did last year.
I
Bet he did.
Doing that
It's just,
over
you'd
and
be
over.
surprised how many times we just stand around and complain
hair.
about all of you. How? They don't even know. The Y-intercept is, you know, I said it a ton of times. We'll see if you remember this next week. I won't. So, 0b, right? 0, comma, that guy right there, because that guy's not multiplied by x, and when we plug 0 in for x, this goes to 0, and all we're left with is. Okay, now let's plug in another number. No, it's just never going to be as easy as 0. 4 is a great choice. 4, right? We're immediately going to move over to x is 4. Okay, we're going to move to the right 4. I'm hinting at this thing called the slope. Okay, so you move to the right 4. Let's see what happens when we get our input here. Y equals 5 over 4 times 4 over 1 minus 3. 4's cancel each other. We get 5 minus 3. Look, that's negative 3. That's the same output we got when we plugged in 0. Plus 5 more, right? Plus 5 more. That's it. Puts us at 2. So if we move to the right, my pen is still down here at negative 3, right? Does that make sense? You hear me there?
Yes.
Negative 3, okay? Negative 3, right there, negative 3. Plus 5. 1, 2, 3, 4, 5. Gets me all the way up to 2. Well, I found 2 points. I know this graph's going to be a line because the function looks like y equals mx plus b. So I could just draw
A straight line.
a straight line. And this straight line is actually, in reality,
A bunch of little points in between.
points, an infinite number of points. Okay? And it's really in realistic reality, it's my guess at where all the other points are going to be. Right? And it's a pretty darn good guess, because I happen to know that this graph is going to have the shape of a line. If I bothered to plot all of the points, and they all melted together and have no gaps in between them, I plot all those infinite number of points, they would all make what kind of a shape?
Straight line.
A straight line. But I'm not going to take the time to do that. I'm going to draw all the points. line, because I just happen to know that about this kind of function. Y equals mx plus b, you're gonna be a line. Okay, let's do it again. For this next function, y equals 2/5 x plus 1. Find 2 points. Let's find the 2 easiest points possible. 1. Okay, let's get things rolling. What's the easiest thing for x? 0. What's that going to give you? 1. Okay.
So no, black.
Well, we've got plenty of time because we saved a bunch of time by plugging in 0. Plug in 5.
Yep.
Okay, let's see that in slow motion here. 5 over 1 is 1, 5, and 5 cancel. We get 2, 1, 3. And we know it's going to be a line because it looks like y equals mx plus b. So, 0, x, 1, y. There's that point. 5 for x. Move over 1, 2, 3, 4, 5. Right? And if I move up 2, up 1, 2, up 2, I'm at 3. And all of the other points, if we were bothered to plot them, would just eventually meld and melt into this straight line. Again for this function. We keep doing it over and over and over until we just start to get so sick of it that we find a nice little pattern, to where we don't even need to, like, in slow motion, plug these numbers into the x. Start with 0. Right? I'll just not even bother with the table. Right? I'll just go straight to the graph. Plug in 0, get out. -4. You can see it in my mind's eye. Plug in a 0, you're going to get out -4. So it's that next point that becomes just a little bit of a challenge. How are we going to find that next point?
Just
Use 7 or something divisible by 7. -3, 7 times 7, 1, is 4, 7 divides 7. We're left with -3 times 1, or 1 times 1, -3 times 4, -7. Which is just 3 lower than the last point we plotted. Send -7. Straight down that.
How do you use 7? Oh, wait, no. How?
How? Okay, so 7 divided by 7 is 1.
Yeah.
Right? We have a negative here. -3 times 1 is -3 over 1 times 1. -3 over 1
Okay.
is -3. And -3 minus 4 is -7.
Oh. Okay, I see.
7, -7.
I thought the -3 and then the -4 was like a point.
Oh, I see. What's that?
I just can't stop thinking about how now every dot is a line, but also a truth, because it's another function that's the product, and that's also parallel to the line next to it, but not parallel to it because they go like that. And then every dot is like that, and it's endlessly cross over each other. And my mind's like, can't handle that.
Well, yeah. The idea of an infinity is a really crazy stuff.
Just like, it's like so, it's like that one dot is just so many things at the same time. Like for another product, it's not even supposed to exist. And it's weird to think to when that dot does not even exist, but it still exists. It's just
This guy is a lie to this function, but it's
Yeah.
true to some other function. Kind of trippy.
my mind's just like going numb from that.
So in this graph, you can see that every time I plug in, say next I plug in 10, and then I would go up 2, next I plug in 15, and that would be 2 higher than the previous point, right? The pattern here is I can just move to the right 5, and up 2. If I move to the right 5 again, which puts me at 10, but if I move to the right 5 and then move up 2, that'll put me at another point. 2, to the right 5, up 2 again, I'll be at another point, and so on and so on and so on. Because every time I plug in a multiple of 5, that 5 cancels that factor of 5 in there, and I'm just left with, be left with 2 or 3 or 4 or 5
So
or
you
6.
can do, so you can figure this out with even 1 point.
With 1 point?
1 point, watch, I'll show you.
1 point.
Put one on the board.
Put one on the board.
Put one on the board.
Y equals negative 5. 2/3 x plus 2. Let's plug in the easiest input that there ever was.
0.
0. We'll get out 2. So 0 comma 2. Well, you kind of negative 2.
Oh, yeah. So it's,
Yeah, but then it would do the same pattern exactly.
But it, yeah, it's just in the air.
So 0, 2, easiest output to find is 0, 2. Now, the next input I want to put in for x is what?
At 3.
3. I want to put in 3. So I'm going to put in 1, 2, 3. But before I even bother putting that in, I know what's going to happen. That 3 is going to cancel that 3, and I'm just going to have negative 5. Right?
Right.
Negative 5 plus 2, which was the y value of that previous point. Right? So I know I'm going to start, when I go to 3, I'm just going to turn that first thing into a negative 5 plus 2. That's 2 minus 5, right? So I'm going to go down 1, 2, 3, 4, 5. Well, that puts me at the point 3, negative 3. And then, if I were to go to the right 3 more, to 6, well, when I plug 6 in here, I know the 6 is going to be divided by 3, and that's just going to leave me with a 2. And 2 times negative 5 is negative 10. So, well, I'm already 5 down from 2. If I move down another 5 from there, then I'll have gone down 10 from 2, right? So I can just keep going down over 3 down 1, 2, 3, 4, 5 more. Right about there. Go over 3 again, go down 5, over 3, and down 5. Because every time I go over 3 more, I'm just going to, this number is going to be the next multiple of 5. Right? This is going to be the next multiple of 5. And I'm just going to, I can start at 2 and move down 5, and down 10, down 15, or I could just go down 3, or over 3 and down 5. So, going over 3 and down 5 is what we call the slope. Okay? The denominator tells me the next x value I want to plug in is a multiple of 3, and it's negative 5 tells me I'm going to just have the next multiple of 5. I'm going to move down in steps of 5. So this is what we call the slope of this line. It has the slope of negative 5/3. So you go over 3 and down 5, over 3 and down 5, over 3 and down 5. You could also go down 5 and over 3, but I think that makes less sense because it's input and output, right? My input goes up 3, and my output goes down 5. Yeah.
So like this is really off topic. How come we don't have school Wednesday, Thursday, Friday?
Thursday and Friday is the annual teachers conference, statewide teachers conference, and Wednesday we don't have school because we have teacher conferences Monday and Tuesday after school. So contractually, we have to be given those hours back since we were here
You guys have to learn CPR.
We have to know CPR every
3 years.
I think it's this year.
3 months.
but that's not, I mean, some people are gonna do that, some people aren't.